much. Take it away.
Well, hello, down at the back. I'll try to talk nice and loud because I know people have been having a hard time down the back. So my name is Luke, and I'm here to talk about how to write a device driver for the Mellanox ConnectX family of Ethernet adapters. And I want to say from the outset here that I don't know how to switch slides. Arrow keys? Thank you very much. So I don't work for Mellanox. I'm not affiliated with any vendor. I'm here in the collegial spirit as somebody who writes software like everybody else in the room. I'm not here to sell you anything. The project that I work on is Snabb. That is a production network data plane that's written in Lua from top to bottom. And the reason that I'm here talking about the ConnectX is that I was very lucky a few years ago to get my hands on the very, very, very first non-NDA copy of the driver specification for the ConnectX. There's a document that had been kept secret for decades, presumably. And the context of that is that I was working on a project with Deutsche Telekom. We needed to run Snabb on 100 gig, and we had a requirement that the Ethernet adapter should not force us into any specific software ecosystem, and it should also not force us to sign NDAs and build our own software based on somebody else's trade secrets. And Mellanox were just the vendor that happened to step up and give us what we needed to do that project. And I think that's a great credit to them. That's why I'm here. So I'm able to talk about this, because I didn't sign any NDA. So my thing is software networking. And I mean this in the extreme sense of doing everything on the CPU, putting nothing on the hardware, not doing any offloads, any of that kind of stuff. I think hardware offloads is yesterday, CPU is today. And it's a really exciting time in software networking now because we're out of the kernel. We're out of all of these constrained programming environments where we can only use very, very specific tools and where everything is different. So now networking software is just software in a very important sense. We have a lot of freedom. And we're taking this freedom in a lot of directions, as we just saw on the ICSI talk. You know, probably some great directions and probably some awful directions. We're doing a lot of exploration now, and we're trying a lot of new ideas, and we're seeing gradually what is it that works well and what is it that doesn't. And I think that to do this effectively, it's really, really critical that we have control of all of the lowest levels of the stack, all the way down to the device drivers. So if we don't have control of that, if we're building everything on large software frameworks provided by vendors, the risk is that we'll have pressure to do things in the way that they've always been done, and we'll get stuck on a local maximum and not see some new ideas. And of course, in an engineering project, very often a local maximum is exactly what you want, but not always. And it would be a real pity if everybody was just sitting on the same local maximum and we never got any new ideas, we would never get any progress. So it's very important that some people are trying new things and they're able to do that effectively. So something I think about these days is what would be the ideal network card for pure software networking. And I think it's actually really easy to describe. The perfect network card would just be a high-speed serial port. We'd take a stream of packets from memory and it would put them onto a network. It would take a stream of packets from network and it would put them into memory, and that's all that it would do. It would not do a single other thing. Any feature that you would give it would be, by definition, a misfeature. Now, nobody makes this network card as far as I know, but it would be really wonderful if somebody would. So if you're a hardware person, please do. But I think for now, the practical thing is to go out and look at what's commercially available that you can kind of use in this way. And for a really, really, really long time, the answer has been the Intel 82599 Niantic. Like, raise your hand if you like the Niantic NIC. You know, everybody loves the Niantic NIC. Not every hand went up, but I know that in your hearts you all love it. Everybody does. So this has been the hacker's favorite for the longest time. There's people like Luca Deri, like, I don't know if it's for decades, people have been doing kind of amazing stuff, all kind of projects with this NIC, and it's just been a great experience, and we've all loved it. The problem is that the Niantic is getting a bit long in the tooth. It only supports 10 gig, it only supports PCI Express version 2, so if you deploy this today, you can't actually take advantage of all the bandwidth you'll find in a modern network or in a modern server. And in a perfect world, Intel would just release a refresh of the Niantic that gives us faster port speeds and gives us parts of the PCI Express endpoint, but that has not been Intel's strategy. So rather, they're introducing a series of other NICs in parallel, and these NICs are not compatible with the Niantic. They need different drivers, and there's not really any one of them that you can point to and say this is the successor to the Niantic. The closest is probably the Fortville, but it's significantly more complex, and it can't do 100 gig, so actually not. So if we want to find the new hacker's favorite NIC here for all of us to do our next projects on in 2019, I think we have to look somewhere else until Intel give us the right thing. And that's what brings us to the Mellanox ConnectX. And Mellanox, as far as I'm concerned, is the only contender, because if you go to the websites of every Ethernet card vendor, it's only Intel and Mellanox where you'll find the device driver specification. So everybody else has disqualified themselves from consideration. And so then if you take a closer look at the ConnectX, it's actually, from a bird's eye view, it's got some really, really, really nice properties, actually. So first of all, the ConnectX supports every port speed you care to name, and they're very, very fast at introducing new port speeds that become standard. So 100 gig, 200 gig, they're on top of all of these things. They refresh the silicon very regularly. You get ConnectX 4, ConnectX 5, ConnectX 6. And they update this across the board. It's not that the 10 gig is getting older and older and then they get the 40 gig. They do across the board refreshes, which is very nice. And the best thing by far is that the same device driver works for every single one of these cards, every port speed, every generation. So if you would take a 10 gig ConnectX 4 and write a device driver for that, that driver could then also be deployed on a 200 gig ConnectX 6. And this is fantastic. This is fantastic if you're a driver developer who values your own time and considers it to be a scarce resource. And the magic that makes this work is that the driver is not actually talking to the silicon directly. There's a layer of firmware in the card that implements a standard protocol and hides the differences in the silicon. So if you're going to write the ConnectX device driver, you will have a controller component, I'm going to call it on the host, that is talking to the firmware over PCI Express and sending a bunch of requests to initialize and configure the network card. And this is basically a CRUD interface that you get from the firmware. You have a bunch of objects like a transmit queue and a receive queue and a flow table and so on, and you can create, you can read, you can update, and you can delete these objects. And you just make a series of these requests to initialize the card and give it the configuration that's going to suit your application. And then having done this, you can then have some logically separate processes that do transmit and receive and multiplex them onto the card. And there's actually quite a neat mechanism for delegating this just with plain old memory mappings. You can delegate access to queues to specific processes. Now, the last I checked, which admittedly is a couple of years ago, the software stack that Mellanox would recommend for building on this is quite large. You have the controller is a Linux kernel module, the MLX5 kernel module, and then on top of that you have the OFED library, Mellanox OFED library, which is a substantial piece of software, and then on top of that you have DPDK, and I don't think it's an exaggeration to say this is about 1 million lines of C code. So it's a considerable dependency to take on. So when we did the driver in Snabb, we wanted to see if we could optimize for making it simpler and easier to maintain, and something that we can understand ourselves all the way through. And so we replaced the whole stack. So we don't use DPDK, and we don't use OFED, and we don't use the kernel driver, and we just talk directly on PCI Express to the firmware. And our driver is 1,500 lines of code, which is actually a considerable reduction from 1 million lines. And in that 1,500 lines of code, it's doing basically 3 things. One is it's implementing the client side of this CRUD protocol for initializing the firmware and giving it an appropriate configuration. It's implementing the transmit and receive functionality for writing descriptors and poking the card, waking it up to process them. And it's implementing multi-process operations so that you can have the controller running in one Unix process, and if you want, you can have transmit and receive functions running in other processes. And I'm just going to give you a really, really quick flavor of how that driver works. So what you see here is on the top is an excerpt from the specification, the PRM, the Programming Reference Manual. So when you look at the specification for the interface to the firmware, you see a lot of tables like this that says if you want to perform the operation set flow table root, you need to create a structure which is a fixed size binary structure, and at specific offsets you need to put certain parameters that the firmware is expecting. It's a little bit like a C struct, more or less. And down below, this is what the Lua code looks like to implement the driver. We have a function with the same name. It takes the arguments as normal variables. It puts them into an array of bits at suitable offsets. It sends this out to the card over a command queue over PCI Express, and it gets a result back saying if the operation was successful or if the operation failed. And like half the driver code or something is just this. So it's 1,500 lines of code, and half of it is basically just transliterated from the datasheet. So it's actually a pretty reasonable protocol. And then for multiprocessing, this is the way that we do it, which might be of interest to other people who are trying to find a simple solution. We have the controller that comes up and it sets up the firmware, and it knows about all of the set of workers that are supposed to exist for the application. And for each worker, it just creates a configuration file the worker then polls for the existence of. And inside that configuration file is all the relevant information, like the addresses in physical memory of the DMA descriptor queues and that kind of thing that they can attach to. So in our implementation, these files are actually shared memory objects, basically C structs. They can be used for synchronization, and we have a trick in Snabb that for DMA memory, we always map it at a consistent address in every process. So any pointer into DMA memory in a collection of processes is globally accessible. And that's like it. That's how the ConnectX driver works, and if you want to write one, I can recommend it. It's not as hard as you would think. So thank you very much for your attention.
We have 5 minutes for questions for Luke.
Okay. So I may start. So you don't want to consider any offload in such a device, but I want to say that this kind of device is able to do some really nice offloading, like tunnel offloading or flow steering, like offloading a full virtual switch, and that's the kind of thing you can get when you use DPDK PMD.
Yeah, absolutely. So if your goal is to actually take advantage of all the offload features on the cards, then the value of the off-the-shelf drivers increases, because the amount of work that you need to do to implement that in a known driver increases. So I think that this approach is very well optimized for a very, very software-oriented approach. If you are thinking of your like a hybrid approach with some things done in hardware and some things done in software, then there's a lot of value. So yes.
And full disclosure, I'm working for Mellanox and DPDK, so I'm available if you want more details or if you want to test this device. I'm available this evening at Man Can Peace Cafe.
PRM.
Sorry?
The new PRM, so the one Luke talks about is the old one. You published the new one.
Yeah, no, not really a new PRM, but there is a work in progress to make things simpler, because you are right, there is a big stack and it is going to be shrinking.
You want to buy PRM? There's more stuff you're just missing.
Anyway, we can discuss detail if you want this evening at the Man Can Peace.
The revolution has started.
You can also lose it on a USB stick there.
Luke, for the sake of the argument, checksums. Don't you want anything from the hardware?
No, absolutely not. So checksum in hardware is a really, really old-fashioned idea. So in Snabb, we don't even use scatter-gather from the hardware. We do everything in unified packet buffers, and if you want to use vector instructions to do a checksum on a CPU these days, it doesn't really take hardly any time at all. And okay, so some of the offloads are quite interesting if you're developing a Unix kernel, because a lot of them have been developed in that sense. So if you're a kernel developer, I don't begrudge you using all of those offloads, but I think for new applications, most of the time the offloads are not really going to be supporting what you want, or you'll find special cases that they don't support and that kind of thing. So specifically for checksums, I think that this is a yesterday feature.
What about segmented transfers into memory? You don't get all of the frame at the same time, but get flits or
so our approach is very simple. A packet is an MTU-sized array. You get the whole packet in, you assume you're going to bring the whole packet into cache. Once you have it in cache, you can do things like checksums on it very, very efficiently. This is the basic programming model that we adopted, and it makes things very, very, very simple. I think it's a slippery slope that when you start trying to offload things in the NIC, then you start saying things like, well, hey, maybe we don't need to get the payload into L2 cache at all. And then you're spending the rest of your life in a balancing act trying to keep it out of L2 cache, because that's going to change your performance characteristics. But if you would just say, hey, let's load the packet into L2 cache, then everything is easy. So I think this is the way to do simple user space network, in my humble opinion.
Does writing in Lua improve the user experience at all? Like, there's been typically it's something like writing vector instructions for DPDK has a very high barrier to entry, for instance. Does Lua help with that at all?
I think that it does. I think that by having Snabb written in Lua, it appeals to a different set of people. I think that DPDK is very well designed for making people coming from like a kernel, VxWorks, and so on background comfortable and keeping things like what they would expect. But there's another group of people who have not been doing networking development because they found it intimidating. They found there's been a lot of barriers to entry. They don't want to write kernel modules. They don't want to program in C. And I see Snabb as catering to these people. So we're really giving an on-ramp to people who kind of were not a part of the networking world before. We give them an easier way to get involved. So in Snabb we do support virt.io, but personally I don't have a lot of nice things to say about virt.io. But that's partly because we have also done the server side of virt.io. And virt.io has a lot of options, and if you want to make all the virtual machines happy, if you want to provide virt.io to DPDK and Linux kernel and so on, which we do in Snabb, it's a huge pain because they expect all of these magical offloads. And if you don't give it to, well, you have to do a lot of work to give it to them. So virt.io is not simple.
So how do you manage to do line break while doing checksums and software?
So in a modern, if you got a modern server with a 100 gig network card and a big CPU, you have something like a 1-to-1 ratio of instructions you can retire compared with bits. You know, so if your average packet size is about 2 kilobits, you can probably retire about 2,000 instructions. If you assuming you're getting good IPC. So basically, CPUs are just really fast. That's the answer. They're just really fast. You don't even need vector instructions.
Thank you so much, Luke.
Thank you.
So next we have